Hey, what's up, guys? This is Sheng here. So, LeetCode number 1964. Find the longest valid obstacle course at each position. Right. So the description of this one is pretty long, but so basically, we're trying to build some obstacle courses. So we're given like obstacles of length n, where the obstacles describe the height of the ith obstacle, and then it defines the longest obstacle course. So the longest obstacle course is basically the longest uh, obstacles on the left side, who is either equal or smaller than the current one, right? Basically, it has to be um, either equal or smaller uh, than the next one, because here it says every obstacle except the first one is taller than or same height as the previous one, right? Okay, so that's the definition of the long obstacles, but I think this one is kind of long, but I think it's going to be easier to look at some examples here, right? So for example, we have obstacles here, and then the output is 1, 2, 3, 3. Why is that? Because at 1 here, the length is 1, right? And because there's nothing on the left side. But for 2, for 2, we have 2, because 1, 2 is the answer for 2. That's why we have 2, right? And for 3, obviously it's 3 because we have 1, 2, 3. And for this 2 here, it's also 3 because we have 1, 2, and 2, right? That can give us like longest obstacles. So then there are like some another examples here, and some constraints. So actually, so after reading this description, you should be realize that this is like a bit of variation of the longest increasing subsequence, right? Basically, it's a LIS. The only difference is that this one is not like increasing. Either it could be equal or greater, right? Because with LIS, everything has to be strictly increasing, right? But for this one, it could be the same, right? So that's the only difference. And plus this constraint, right? With n of n, so we need with this 10 to the power of 5, we cannot use n squared, because since we already figured out it's LIS with a little bit of variations, the naive solution for LIS is going to be a dp, right? With n squared time complexity, where for each of the I here, we will check all the previously dp values, right? And then we'll get the minimum. We'll get the maximum among all the previous dp values, right? But that will be a O of n squared. So which means for this one, I believe I have already talked about there's like a n log n solution for this LIS, where we'll be using the binary search, right? So basically, we binary search the dp value here. We have a dp array here, right? So we do a binary search on this dp array here with the current value. Basically, if the index is within the size of the dp, then it means that we can insert it, right? And then when the index is outside of the dp of the outside of the dp array here, it means that we need to increase the dp, which and in the end, the length of the dp array will be the longest, will be this LIS we're looking for, right? So for example, let's use an example to explain this. Let's say we have 3, 1. Let's say that we have to do this 3, 1, 5, 6, 4, 2, right? So if you're only talking about LIS, right? So for this one, we have a DP here, right? We have a DP value array here. So at the beginning, if we do a binary search on this one, obviously we get an index, but the index will be greater than the DP size, right? So that's why we're gonna insert this one to 3 into the DP, right? So now we have dp equals to 3, right? And then we have 1 here, right? So if we do a 1, is do a binary search on with 1 on this dp array here, what will we have? We'll have 0, right? Let's say we're talking about binary search bisect left, okay? Whenever whenever index is within the dp, we update this value with 1. So which means that for 1, we'll have dp equals to 1, right? And then when it comes to 5, right, what we have 5, if we do a dp a binary search on 5, 5 this one will get the index will have what? The index will be 1 in this case, right? So that's why we're gonna extend this dp array to 1, 5. Okay, and then for 6, again, right, this one gonna be a 1, 5, and 6. Okay, right, and then what? And then 4, right? And then we have 4 here. So if we do a 4, the index will be what? The index will be 1, right? Because since we're doing a bisect left, that's why for 4 we're gonna update index 1 with this number. It's gonna be 1, 4, and 6. Similar with 2. With 2 we have like what? It's gonna also be index is gonna be 1, right? So you have 1, 1, and we're gonna update this one with 1, 2, and 6. Okay. So basically, we use the binary search to track the basically to track the smallest, right? To track the smallest value at each of the index, so that later on, if we have another values greater than 2 here, we can try to increase that later on, right? Because now we know that at index 1 here, the smallest is 2, right? So if we have some bigger number after this 2 here, we can append this one to here. And then in the end, the length of the LIS will be the final answer. So that's basically the binary search solution for the LIS. Okay, but as you guys can see, we use a bisect left because we're looking at what strict increasing, right? That's why we have to do a bisect left. But for this one, the only difference is that we also need to consider the same value, right? To this into this bisect binary search. So what does it mean? All we need to do is that instead of a bisect left, we just need to do a bisect right, right? Because for example, we have 1, 2, 3, and 2, right? If we use the same logic here, dp of dp, right? So at the beginning we have 1, right? And then we have 1, 2, and then 1, 2, 3, right? 1, 2, and 3, right? And so now we have 2 here, right? So when we have 2 here, if we do a bisect left, right? So then what will be the index? It's going to be 1, right? But instead, what we need is instead of 1, we need 2 because 1, 2 also counted as part of the longest obstacle course, right? That's why we need index 2 here. So that's why we're going to do a bisect right. And as you guys can see, actually, the index plus 1 will be the answer for us, right? For each of the index. Right, because for the index we have 0, right? We have 1, and then we have 2 and 2, right? If we do I plus 1, then this is our final answer. So that's it, right? I mean, as long as you can figure out this is a bit of variation of LIS with the binary search solution, everything should be pretty straightforward, right? So we have this one, obstacles. Actually, we don't need n in this case, okay? So all we need is a DP, right? So let's say we have a DP array, and then of course we need an answer array as well, right? So for obstacles in obstacles, right? So we have index, right? Index is going to be a bisect. Like I said, it's going to be right, right? We search the DP with the final obstacle, right? Okay, if the index is smaller than length of DP, okay, we do a update, right? Index equals the obstacle, right? Else we do a dp.append of this obstacle, right? And then the only thing left is that we just need to use the index +1 to update the answer, right? Index +1, okay? And then return the answer. So that's it. Okay, cool, right? So this one, no, this one is not that hard. But I think the only thing is that you have to be realized that first, this is an iOS problem. And second is you need to know there is like a unlog n solution for it, given the constraints here. Otherwise, it will TLE. And the last thing is that uh, so this is a little bit of variation of the regular iOS solution, where we have to consider also uh, consider the same number, right, into the final answer. That's why instead of bisect left, we need to use a bisect right. Okay, and then that's it, I think. Cool. I don't think there's anything else I want to talk about for this problem. I'll stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.